Let's get right to it. So, this is the last one, and for now, and today we're gonna talk about scalability and oracles. And scalability is really an important matter when it comes to blockchain because there is this conception that blockchain cannot scale, and I mean it's kind of true in a way, no? Because as we saw already from the first class, like blockchain allows. Okay, sorry guys, this is not the right presentation. I'm gonna take the presentation in English. So scalability is really a big problem, like in blockchain, because there is a limit on how blockchain can scale and how many transactions can fit, in a block. And at the end, this is related to what we saw in the first class already. So blockchain at the end allows you to have a decentralized and immutable ledger, and the fact that every node needs to store the state of blockchain at the end makes it very difficult to censor, no, or shut it down. At least public blockchains, no, and everybody can download the software. You can set up a node, and until there is at least one node that replicates the ledger, then the blockchain exists. And this is the power of it, no? Because it makes it almost impossible to shut it down and or to censor it. And the way this is possible is because at the end every node replicates the state of the blockchain, no? So there is a very high redundancy of the data that it's on the network, because every node will need to have an exact same copy of all the other nodes. So the feature, no, that allow blockchain to be extremely difficult to censor, shut it down, and makes it decentralized, so difficult to control, is also the same feature that at the end makes everything clogged, because it's really the most inefficient database ever, no? Because every node, every computer needs to have exactly the same data, exactly a copy of it, no? So this freedom, no, and decentralization comes with a cost. That the cost is scalability, no. So what on one side makes it secure and decentralized, on the other side it makes it extremely inefficient. And there are blockchains that advertise themselves as extremely scalable, and they claim they can process thousands of transactions per second. And at the end, this can be also true, but also, like as we saw already, sometimes we always need to remember the blockchain trilemma, which I hope now you get used to reason with it. And so at the end, what it means is there could be blockchain that advertise themselves to be extremely scalable, but usually this really comes with a very high price, which is centralization, no, or maybe a lack of security. So at the end, when we talk about blockchain scalability, we're talking mostly about scaling public blockchain, which is at the end the only blockchain that makes sense to scale, no? Because the others, I mean, if you have a permission blockchain, like you really can scale it however you want. At the end, you have your nodes that control the network, and it's easier to scale at least. And even though, no, like blockchain is extremely secure and decentralized, the public blockchain still they come with a very big limit, no, that is the scalability. And we can see this like in 2018, as you see, these were the fees in dollars for a Bitcoin transaction. It means you could send €1 worth of Bitcoin to another address, and maybe you would pay 45 euros, I mean dollars of fees, which is like unbelievable, no? Is not very usable, no, as a network. And so it's needed to scale, and the debate on how to scale is very heated, especially for the Bitcoin network, and it's very heated exactly because of this blockchain trilemma that we saw. That on one side you have decentralization, on the other scalability, and on the other security. So scalability comes with a compromise at the end, starting in public blockchains, and it's very hard to set a limit on which compromise you should accept as a community, and which compromise you should reject in order to scale. No, so for years, part of the community of Bitcoin pushed to change the Bitcoin consensus mechanism to accept bigger blocks, which at the end is the rules, no, that the network participants, the users, they set between themselves. No, in the consensus mechanism, they say, okay, look, we're gonna use these rules, and then if there is a community that wants to change it, in this case, a community that wants to propose to just have bigger blocks, then I mean it's a big deal, no? Because you can have very big consequences. And right now, a Bitcoin block can contain up to 1 megabyte data worth of transaction, which is not a lot if you think that it's a huge network and is getting used more and more and more. And this at the end was no, one of the reason why this community, this part of the community, was pushing for bigger blocks. They were saying, hey, but why let's not just double the size of the block to 2 megabytes? Like if the block is bigger, then more transaction can fit into a block, and so transactions can be approved faster. And because at the end, we saw that in Bitcoin in general, we need to expect a time from one block to another of around 10 minutes. So if you need to wait for every block to come 10 minutes, then it's good if they're big, you know. This was the argument, because then you could fit more transactions, and the miner could process things faster. Seems a very nice solution, seems very easy to implement. At the end you change a number in the code, and the problem is that increasing the size of the block then would make it very difficult for normal users to validate the network. So it's already difficult now because of what we saw when we were talking about difficulty adjustment. So there is a lot of people who now are validating the network, and for this reason it's more difficult for you to be the lucky guy that gets the right hash to propose the block. And on top of this, if you have even bigger blocks, then wow, it's even more difficult for users that have a normal computer to validate them. And at the end, this can bring centralization, no? Because big miners would be happy because they would process transaction faster, and there would be also less people in the game, no, to mine blocks, so more money for them. But this is a very high risk, because at the end you end up in a oligopoly, no, like we saw some classes ago, and this can bring up a risk of censorship and denial of services and shutdown and all these kind of things. So this part of the community, they tried several times to raise the Bitcoin block size, and raising up discussion, raising up votations, and all these kind of things. And in general, when people try to raise the Bitcoin block size, it always end up with hard forks. That we saw is basically a split in the network, in which the two networks are completely different because they follow different consensus rules. So what is truth for me is not truth for other people that follow other consensus rules. So we're basically splitting the network, no? And this is in general what has always happened when it has been tried to propose higher blocks. And this is because, as we saw in one of the first classes, it was very difficult to make this argument of raising the block size would be accepted by the whole community. And because of this implication and this higher centralization. So also, like, Bitcoin is important because it's the first one, and in general, like, people that get into Bitcoin, they would like that rules are the same, they don't change. And This is because if rules change one time, then they could change also another time, and another time, and another time, and then nothing prevent that rules keep changing, and maybe they don't change for the better. Maybe changing, there are some side effects that bring centralization or less security and all these kind of things. So this is also the reason why it seems, that Bitcoin community as a whole, they try to stifle innovation in a sense. Not because they want to stay with an outdated network, but it's because when you make some very big change in the code, and when you have already a lot of money and ecosystem built around this network, then there are a lot of risk that if you change something that not the way it's supposed to work, then everything goes down, and this can be a huge problem, even bigger than not being able to scale. This is the reason why it has been very difficult in general to propose big change in the Bitcoin network, because changing the heart of it and the consensus rule would actually bring some risks, no, in the equation. Some security risks, some risk from game theory that you may not consider, and these kind of things. So like Bitcoin is nice because it's immutable, and also the consensus is thought to be the same. So this is the reason why the majority of the community didn't accept this proposal of changing the block size and incrementing it, because this would imply more centralization, and of course is not the network we signed up for, no? So it's very risky. And the more the consensus rules stay the same, in a way the better, no? At least the core of it, and because this would prevent some communities to take over Bitcoin, and uh, and uh, and this is more or less the reasons. And anyway, we need to scale, no? Like it's extremely important. We cannot pay $45 of fees when you transfer $5 of worth of Bitcoin. Like it's unfeasible, no? And for this reason, different ways have been proposed, no? And depending on the protocol that we look into, like there are different ways to scale. When we talk about Bitcoin, one proposal that in general has taken up more traction is the Lightning Network. And the Lightning Network is an off-chain scaling solution made just for Bitcoin. So it's kind of a layer 2 solution if we consider the layer 1 to be the Bitcoin blockchain. And this means that you can basically scale because you kind of perform computation outside of Bitcoin, and then you kind of merge it together into one transaction, and you kind of create some checkpoints, no, in a way in the Bitcoin network. And this allow you basically not to do every single transaction on the blockchain, because sometimes there are stupid transactions like €1 too. Like, why should you put every transaction on the blockchain if maybe you can put a lot of transaction outside the blockchain, and then every now and then you merge them into one single transaction. And this is exactly the way how Lightning Network works. So through Lightning Network, users have basically off-chain ledgers between them, and they basically take notes of every transaction that is happening between them. So when it's needed, like all these off-chain transactions are condensed into one chain, into on-chain transaction, and so just one transaction can represent a lot of transactions that are not handled on the blockchain directly, but are handled in the blockchain through this synthesis, no, of transaction. And this comes a little bit with the concept of payment channels. So Lightning Network works with payment channels in the sense that two users can make thousands and thousands of transactions between them, taking note of this transaction off chain, and then condense them into just one transaction. And this at the end is good, no? Because like imagine you can take out thousands of transactions outside the blockchain, and just every now and then put some transaction that synthesize the whole thing. So it's quite powerful concept. And The way it works is the following: like two users that wants to create a payment channel between them, they put some bitcoins, no? So they have bitcoins, and maybe they have 5 bitcoins, and they put it in the middle, at the center of the table. So they don't put it on the blockchain necessarily, but they put it in a way that none of them can actually get them without the allowance of the other, no? If this thing is not true. So it's slightly different than this, because usually just one of them, just one of the user put all the money, and this is for technical reason. But in general, we can kind of understand it like this better, and this is exactly how it works, more or less. So this money gets in the center of the table, so none of them can now take it whenever they want, like because of if they try to fake, no, the balance of the network. And they just keep an accounting between them. So let's say they have a piece of paper, and where it's written that Lisa, for example, owns 5 bitcoins and Bart owns other 5 bitcoins, but the bitcoins are at the center of the table, like they are kind of in a contract, no, between them. Then if Lisa wants to give a bitcoin to Bart, then she can simply update her off-chain ledger and saying, okay, look, now I own 4 bitcoin and now Bart owns 6 bitcoins, because Lisa give 1 bitcoin to Bart. But the bitcoin at the center of the table, they never move, they always stay there. So it's a ledger that gets written, and if Bart wants to give half a bitcoin to Lisa, then they write it in this off-chain database, no, the update of the balance. And then if Lisa wants to give 3 bitcoins back to Bart, then you can see, Lisa now owns 1 bitcoin and a half, Bart owns 8 bitcoins and a half. Then whenever they want, like some of them, they can submit the state, no, the current checkpoint of the balance they have, and then the bitcoins that are the center of the table are sent to the respective balances. And there are some problems of this, and one of these problems is that you need to have a payment channel established between the person you want to make a payment to. So it means at the end, like we see here, they need to put money at the center of the table, and this is a payment channel, and this is the only way for them to make off-chain transactions through the Latin network. So they need to block some money into a payment channel that they want to have with a person. But the problem is, what if Lisa and Bart, they don't have a payment channel between them? They will need to block money, you know. And I mean, it's a bit of a, not of a problem, but it's a bit uncomfortable. The good thing is that maybe if Lisa has a payment channel open already with Homer, and Homer has a payment channel open already with Bart, then Lisa, through the payment channel that she has with Homer, she can reach to Bart, just because Homer also has a payment channel open with Bart. So they can still handle payments off-chain indirectly if there is a connection of payment channels between them, and there can be a lot more people in the middle. Another problem is of this solution is that you need to have kind of watchtowers, like you need to constantly look at the payment channels and be sure that nobody cheats. So you need to be sure that nobody puts in the network, in the blockchain, a transaction that is not supposed to be there, maybe because it's a double spending, maybe because this money is not true or whatever. And so you need to always be aware that like somebody could cheat you out, no? And you need to constantly watch the network, and if you see somebody that is trying to scam you, then you submit your version of reality, and then at the end this person gets penalized, so you get all the deposit that he put also. So this is kind of powerful, no? Because until there are people who watch the network to prevent users to scam other users, then scammers will be penalized. And actually there are watchtowers that make this service, like watching the networks for scammers to try to submit transactions that are not true, and they take a small fee of the money that they recover to you. But still, you will need to check up constantly the network. And this is a picture I like. Like, I think it's a nice picture because it's the state of the Lightning network some time ago, and it's constantly growing. And as you can see, like, it's everything is connected, no? So there are some clusters which could be maybe exchanges, no, that they need to process huge amount of transactions between them. And in general, like, he's kind of he's very connected, no, a lot of channels going on. So this is how you could visualize the Lightning network. Regarding Ethereum, there is a solution that is extremely similar to the Lightning network, and this solution is called state channels. And this works basically the same way that it works on Bitcoin, no? The Lightning network. So it's kind of at the same problem of the Lightning network. You need to always constantly watch the blockchain to be sure that nobody cheats on you, and you need to have a payment channel open with the person you want to pay to. But if somebody has it with this person and you have with this person, then you are already done. So maybe it's not even a big deal. Sometimes there are exchanges that have payment channels open with everybody. So still they are not so big problems in a way. So it's just a thing to consider when we talk about the drawbacks, not the catch of implementing a scaling solution or another, because in general, like, there are always gonna be pros and cons. Another solution that this is on Ethereum as the state channels. This solution, they say, okay, let's create side chains. Like, let's create some child chains, like some chains that are child of the blockchain, of the main blockchain, the Ethereum one, and they kind of run on the side of it, like if they were child of them, and like you can make transaction over these smaller blockchains that depend on a bigger blockchain that is Ethereum. And if something goes wrong, well, you still can roll it back into the main Ethereum blockchain and be sure that your funds are secured. So mm, it's kind of similar, no, in a concept to the state channels, in the sense that like you still have a way to go back to the blockchain, no, to like put the checkpoints on where the truth is. And this is in general like the common element of every scaling solution. The fact that if something bad happens because you are off chain, then you can roll it back to the last moment in which everything was still going good. So of course, like, transactions are faster in the child chain because there are multiple chains, and at the end the transactions are not clogged, no, in just one chain. So every now and then, like, you can have checkpoints recording on the main chain. If the child chain gets attacked, then transaction on the child chains are reverted, and this story goes back to the last moment in which everybody agreed that that was the truth, no? And this solution is called the plasma, and you can visualize it like this: like you have the main chain, the Ethereum blockchain at the top, and then from that you can have different child chains that they perform transaction independently. Maybe, you know, for maybe there is a child chain for a gaming application, no? Or maybe for an exchange, or and at the end, like, you can make the transaction on the child chains. They are less secure, but still you accept this risk because you know you can roll it back to the blockchain whenever you want. There are some problems here also here because users need always to be online also here. Like, they need to check that nobody cheats on them. And also, like, users need to store some data, no? Because at the end, like, uh, you know, it's another blockchain at the end. So it still is other data that an user needs to store, no, in a way. And another solution that is very nice is called the rollups. This is also for Ethereum. And in general, rollups is a solution that is pushed a lot by Vitalik Buterin, that is the founder of Ethereum, one of the founders of Ethereum. And in rollups, what happens, like funds are blocked in a smart contract, and then there are off-chain commitments that are made to the smart contract. So you like say, hey, I see that in this off-chain database, then there are some transactions and these kind of things, and okay, let me merge these transactions into one, and let me commit this change, this proof to the smart contract. So you basically gather all transactions together, and then you commit just a synthesis of it to the smart contract. And these changes are represented by a proposal for a state change. So like you can see transactions that are off chain, no, in Ethereum, and you can take them, gather them, and you say, hey guys, I looked that the network changed this way. This is my proposal to change the state of Ethereum through this transaction, like this. Because at the end, like if you remember, blockchain is not only a decentralized database. Blockchain is a state machine. It's a decentralized, deterministic state machine. Like a transaction changes the state of this decentralized network. So at the end, you can make a proposal, no, and this proposal can be a transaction that say, hey, I would like to condense all these changes that have been in the network into this transaction. And most of the data is stored off chain, and it is committed now into the smart contract, and the smart contract makes reference to this off-chain data that is held in a database, for example. And the smart contract is what holds all the funds, and and takes notice of these cryptographic commitments that are made, no? So he makes this reference to this off-chain state that is can be accounts, balances that are stored off-chain, no? So maybe in a shared database or whatever. And there are two different types of rollups, and one is optimistic rollups, and another one is zero knowledge rollups. And an optimistic rollups, what it happens is like the new state is published by nodes, and in general is assumed to be correct. This is why it's optimistic. Like you don't assume that people are trying to cheat. And the reason that this happens is that at the end, the smart contract doesn't check if the cryptographic commitment you do is true or not, like if you are cheating or not. Like the smart contract doesn't automatically check. This is why it's optimistic. Like it starts with the assumption that you are behaving good, but everybody in the network can look that you are trying to cheat it, and then it can submit a notification to the smart contract, and then the smart contract see that what is being told is not true, and then he penalizes the cheater, no, and preventing him to take every fund that he put on it. And so the transaction gets reverted and the attacker gets penalized. Game theory, like you avoid people cheating because you have other people that gets maybe some reward in protecting the network to do so. At the end, similar to state channels and Lightning Network, like you need to be online to catch the attacker. Like if you assume it's optimistic, if you assume like nobody's gonna cheat and you don't check, then bad luck, because there's gonna be somebody who's gonna cheat. But the assumption of this is that enough people are cheating all the time, not cheating, checking that people will cheat all the time, and this is how you prevent, the people to cheat and the blockchain to not represent the reality. So at the end there is always need to be this checking, every time it seems you have an off-chain solution, like there needs to be a check, and they need to also execute every single transaction. Like the nodes need to check every single transaction, and see if these transactions are valid or not. Zero knowledge rollup, on the other side, is similar to optimistic rollup because you have a smart contract in which funds are held, and there are cryptographic commitments and all these kind of things, but is the smart contract that automatically checks if transactions are correct. So in zero knowledge rollups, a smart contract does not assume that who proposes the change of the state of the blockchain is saying the truth. And so in zero knowledge rollups, like operator generates zero knowledge proof for state transitions, and we saw more or less what was a zero knowledge proof when we talked about SSI, like self-sovereign identity. And these transactions that are submitted are verified by the smart contract, and then the zero knowledge proof, what it does, it proves that exists a series of transactions correctly signed by owners, no, by the person who make this transaction, and then it gets updated, no, and then the account balances are updated in the way they should be. So at the end, with these cryptographic commitments, these zero knowledge rollups at the end make sure that the blockchain gets updated, that a lot of transactions are condensed into a commitment, and that still nobody cheats, no, on this. And so it's kind of a way of snapshot, like you see the state before, like you take a snapshot and you see the state later with another snapshot, and the thing that changed the state of the blockchain is this commitment that is verifiable with an hash on the blockchain. So like maybe there is an user, and she has she has seen a lot of transactions that she would like to submit, and then she gathers them, and then you say, okay, after these transactions, then the state of the blockchain would be updated like this, like all the balances would be like this, and the accounts would be like this, and all these kind of things. And so after she gets these transactions, she makes a cryptographic commitment, and then the blockchain state change from one block to another, like to the new state that this cryptographic commitment say, no? There is a problem, like there is always a problem, like as we kind of understood, like every solution in blockchain, it comes with a compromise, and the compromise of this is that zero knowledge proofs, especially snarks, they require, which is a specific type of zero knowledge proof, they require an initial trusted setup. So this could kind of bring some centralized environment in just the moment of creating the zero knowledge proof at the beginning. And this is because it's needed a trusted setup, so a framework of trust between people in order to set up the seed to later on create these proofs. So there is another solution which is very interesting in Ethereum, and is sharding. And Ethereum is not the only network that uses sharding, but this is the most not interesting, but is the most famous, no, in a way. And sharding promises really high scalability when Ethereum gets updated to 2.0, and it can achieve because Ethereum is not gonna work anymore on proof of work, but it's gonna work on proof of stake. And the fact that it changes this part of the consensus mechanism, it's gonna allow to divide the network into pieces, into parts, and these parts are called shards. And every shard will have their own group of validators. So every part of the network, every shard will have a group of nodes that validate just everything that happens in that specific part. So it means that nobody is required to validate all the network, all the transaction of all the parts of the network. So this is good for scalability, because at the end you are kind of saying, hey, you're a node, that's perfect. You don't need to replicate all the data of all the blockchain. just mind your own part of the network and validate that, and then other people are gonna do the same in other parts, and then together we found ways to connect this knowledge, and at least it allow us not to burden all this um, all the nodes to verify all the transactions, no? So a group of nodes will validate the transactions of the shard that they are assigned to. So they are assigned to a shard, and every 10 minutes more or less, and the shard in which you are assigned to as a node is as a validator is given by randomness. It's very random, and randomness is essential. Like, is the whole security of this change of the network is that you don't know which shard you're gonna be assigned to until the moment in which you are assigned to that shard. And the reason for this is because if it wasn't random, so if you knew in which shard you would get to validate transactions in, I don't know, the next hours, then there are some risks in which some nodes that are malicious, they could collude between them and know in advance that they will be assigned, for example, to the same shard, and they could collude and they decide that they want to take down the shard. No, they want to approve transactions that are not relevant to the truth and to the consensus mechanism and these kind of things. So a shard is just a part of the Ethereum network, and it means it's easier to attack a shard than the whole Ethereum network. Like, at the end, it's just a part of it, and we saw that, like, as a validator, you would just validate the transactions that happen in a single shard, and this at the end is risky, because now you don't have all the nodes that validates all the transactions. Like, now you have some nodes that validate a part of the network, some other nodes that validate another part of the network. And the problem is that if just a shard is under attack, then the whole network indirectly becomes under attack, because every shard is connected at the end of the day, through the blockchain. But it's easier to attack just a part of the network than the whole network. So it's kind of tricky, And for this reason, is they are taking a lot of time to make the change from Ethereum to Ethereum 2.0, and there is a lot of work going on, and this kind of network partition could bring a lot of scalability in it, but it needs to be done properly with the right security and the right considerations, because it's kind of tricky, as we are seeing. But on the other side, you don't need to have this extreme redundancy of data between nodes, so this helps in the scalability. And even if your node will just need to have the information regarding to the shard in which he is assigned to, and some other shards, maybe the shards which he comes from, still there are some nodes that can still, you can have all the information of all the networks. Simply, it's gonna be a lot, and this will be kind of super nodes, in a way, like the nodes that will do just that. And there is some concerns in a way that this could bring some centralization of information, but on the other side, there is also trust that this change will be done good, and so still you can have your super node if you want to. Just, it's not necessary for you to have it, and this is most probably the reason why you won't set it up, but you can do if you want. Ethereum is not preventing you from seeing the whole history that happens in the whole shards. And the elements that connect the shards between them is called the beacon chain, which is the layer where randomness happens, so where validators are assigned to a shard or another every 10 minutes. And the beacon chain is also what makes the communication between the shards possible. So if there are, for example, transactions that happen in a shard, if I'm a validator of the shard, then I can see, if they can be approved or not, but I'm just the validator of one shard, so it's not possible for me to see and to approve a transaction that goes from one shard to another, because maybe I don't have the full history of the other shard. And the way that this inter-shard transactions gets carried on is basically through some receipts that goes through the beacon chain, which we kind of can imagine as the blockchain as we think of it. A way I would like to visualize it is more or less like this, like every block, or every now and then, like there are some new shards. Like the shards are always the same, but there are validators that change from one shard to another to approve, and so they kind of switch between themselves into this randomness mechanism, which prevents collusion between validators, and they can relate through the beacon chain, sending receipts on what happens and communicate between their shards. But the main transactions are done inside the specific shard, no? Because the shard you divide the network because you expect that some nodes will talk more between each other, so maybe you divide like this, and like there are ways not to divide the network. This is a more technical way to see it, and as you can see, like the beacon chain is connected to the main chain, like to the blockchain, and it's just this layer that provides this randomness and these receipts, and it's also the layer that is directly connected to the main chain, to the blockchain itself. So at the end, the blockchain is just gonna be the reflection of what happens in the beacon chain, because the beacon chain is what is gonna handle all the shards, no? And on this shard, on every shard, then there's gonna be the Ethereum virtual machine, also the logic of Ethereum, that smart contracts and like everything that will happen on Ethereum, it will happen on the shards. This is another way to see it, very trippy, I would say. And like the blue chain is the beacon chain. Then there are these more clear chains that are shards. No, they are shard chains, because at the end also the shards have kind of their own blockchain at the end. And then there are some connections, no, between the shards and the beacon chain, and this is what makes everything possible for the network to go on. It's this is the reason why it's getting complicated, like to understand Ethereum, like it's and it's always gonna be like this, because the protocol gets evolving, and like it's really crazy. Like the huge majority of people, they really don't know what's really happening technical wise in Ethereum, even the very high skilled developers, just because it's literally a world supercomputer. Like it's really too big for everybody to know everything of it. And it's not clear, like through which criteria Ethereum will will be divided into shards, because at the end there are different ways in which you could think of dividing the network in shards. Like one option could be to have in the same shard, for example, all the nodes that are geographically near to each other. No, so you want to have fast transaction. Maybe another way is to get all the nodes in one shard is to get all the nodes that talk a lot between each other, and this is the way that maybe you would say, okay, it makes sense that in one part of the network there are just nodes that mostly talk between each other, no? For example, so some exchanges and these kind of things. Also, there is another way you could think of dividing the network into shards, that could be for similar services. You could have a shard for gaming, you could have another shard that just perform decentralized finance services. And at the end, there is not a right or wrong solution, because as we have been seeing so far in every piece of blockchain that we have commented, like there are always pros and cons, and there are always consideration to make and consequences. So the way to divide it is still getting discussed in this moment. And we saw there are different ways to achieve scaling, both on chain and off chain, and none of them is perfect. And like usually it's a combination between ways that it can help to do everything. Like Plasma can work with sharding, and we then can work with state channels, and all this solution together can help, for example, Ethereum to scale a lot. And this is more or less the ways that are now out there to scale, and most probably other ways are gonna come, but these are the ways and that in which there is most development and most results going on at the moment. There is another part of this class, which are gonna begin now, that is talks about oracles. And oracles is quite an interesting topic, because oracles are the way in which non-deterministic data can be appended into the blockchain. What do we mean by this? Well, you remember we discussed that blockchain is a deterministic state machine. Like blockchain is deterministic because from an initial condition and applying a transaction, you can definitely get a state that cannot be different from one node to another. Like every node getting the same condition and getting the same transaction will get to the same exact result. And this is where determinism applies to blockchain. So there is no way in which with the same initial condition and the same transaction you can get to different results. And this is what blockchain provides you. Like this immutability, this security, that nobody has a different version of the truth. But still, so could we make a smart contract that performs some logic depending on how the weather in Barcelona is? Yes and no. Like in theory, no, because for example, how could you do it? Like different nodes can connect to different websites of weather providers and different sensors that tell them different weather in Barcelona, and they could have different results. So it is not deterministic at all. Maybe even if they connect to the same website, maybe a node could have some delays, some internet connection that is not going good or whatever, and they could still get a different result from another node that connect to exact same website. And this is a problem, because then like you don't have an initial condition for every node, so you cannot, if you cannot agree on the state of the network or what happens, like how can you perform a transaction or some logic to get to another state if you don't agree in the beginning of it in the first place? Like it's not possible, no? So this difference of result that nodes may get from different outside the blockchain, let's say, is not compatible with the determinism of the blockchain. So this is where the problem comes from, and the smart contract lives on the blockchain and therefore are deterministic, and they cannot act on behalf of non-deterministic data. They can just act when they can receive a valid transaction, and then they perform some logic according to what they have been programmed with. But they really cannot get data and do stuff with it like this. Is not possible. You cannot get data from a sensor and put it in the blockchain directly. This is a common misconception. You really cannot do it. The only way for you to do it is to bundle it inside a transaction that a node puts in the network and somebody else validates it. If you put it in this transaction, then the smart contract can digest it, because a transaction is deterministic, is valid or not. Like it does not depend on anything else. It's like, okay, do you have money in the account? Yes, you can do the transaction. No, you can't. And if nodes start with the same condition, they know exactly on the network what is the state of the balances and the accounts and the stuff like this, then they can agree on the same result if a transaction is performed. But the weather in Barcelona, the result of a football match with the president of the United States and so on, is not deterministic data. Is really not deterministic data, because somebody can connect to different service provider, get different data, maybe get some delays, and it's not possible to put it plain like this on the blockchain. So this type of data needs to be kind of translated into a transaction in order for a smart contract to digest it. And this is where oracles are useful. This way, like through oracles, we can put non-deterministic data into the blockchain and perform logic for it. And the way we do it is through oracles that are basically nodes that get some non-deterministic data, so off-chain data, into the blockchain through transactions. If the data that they put in the blockchain is not true, then some other nodes can notice it, and they can say, hey, this oracle is not behaving correctly, like it tells fake data and these kind of things. And the loss of credibility for this oracle like could have some negative consequences, no? So like oracles are kind of incentivized to put the they are kind of incentivized to say the truth, no? And after the data has been put in the blockchain through a transaction made an oracle, then it can be digested by a smart contract, but not before. And a cool project is ChainLink, that basically aims in creating a network of oracles, rewarding every oracle for their work if they work correctly. And their work is basically gathering data from APIs of, I don't know, financial markets and all the kind of service providers of data that you can imagine of. And you can actually set up your oracle and you can gather off-chain data and you kind of notarize it, in the blockchain through a transaction, and you can be rewarded for it. And this is how this ChainLink works. So they gather all this different data from retail payments, PayPal, Visa, MasterCard, other bank payments, and they can get market data also. They can get data from events, from whatever, from literally whatever. Also other blockchains. So it can be also a way to connect different blockchains between them, which is kind of powerful. And this is quite interesting. And like oracles are gonna be extremely needed, because at the end there is no point in having smart contracts if you don't have any data that is on the blockchain to perform logic in. Like you need to have a confiable, a trustworthy source of data in order to perform logic in through a smart contract. And so it makes sense that oracles are rewarded for their job, and that a network is created for this reason.